Alright, in this video we're going to introduce recurrent neural networks in Keras, and in particular talk about LSTMs. As an application, we're going to classify sentiments from movie reviews. So there's a few architectures available for recurrent neural networks in Keras. The first one is a class called simple RNN, which is a basic plain on-the-nose recurrent neural network which suffers from problems like vanishing and exploding gradients, so you see this very rarely used in practice. Instead, a gated recursive unit introduced in 2014 has certainly its use cases. Also, LSTM, or long short-term memory models, introduced in 1997 by Huffington Schmidhuber. Those are the most popular recurrent neural networks with Keras and maybe overall. So oftentimes when people talk about using RNNs, usually they mean applying LSTMs. We will focus in this lecture exclusively on LSTMs. Alright, how do we build LSTM layers with Keras? There's a few things we have to specify. Recall that with a LSTM layer, you have two sets of weights. First, a regular set of weights, and then also a recurrent set of weights. So in Keras, that's called recurrent kernel. And apart from specifying the units, so the number of output units and an activation function for our layer, we also have to specify everything recurrent. So for instance, we need a recurrent initializer, a recurrent activation, and so on. So if you want to specify a regularizer or a constraint, you can do that. Something of note here is that LSTM layers allow you to specify a dropout within the layer. So you don't have to specify a dropout layer separately, but you can specify a dropout rate for an LSTM, both for the regular set of weights specified by dropout and for the recurrent weights specified by recurrent dropout. The last keyword we want to mention here is return sequences, which is set to false by default. So what that means is, if you set it to true, then the return value of your LSTM won't be a simple vector, but a matrix instead. So how you run an LSTM is by you apply different time steps, right? You go through different time steps, and at the end, the output is one vector usually. If you set return sequences to true, you will also get returned all the intermediate values, ending up at a matrix then. Okay. To compute our application, we need to introduce another layer, which is quite useful for many such applications. And so embedding layers are used as a very first layer only in Keras. And what you use them for is you transform integers into vectors of the same length. To give you one example, here's two numbers, 3 and 12. Those could be embedded into vectors of length 2, shown on the right. A prototypical example that you would apply this to, and which we're going to do, is you want to embed a certain vocabulary into a vector space, meaning each word in this vocabulary has to be embedded or has to be given a representation in that vector space, and then you apply those embeddings to sequences of words. This way, you can map a 2D input to a 3D output, which connects to an LSTM. So meaning, if you have a mini batch of sequences of IDs, you can map those to a mini batch of sequences of vectors, i.e. a mini batch of matrices. And this can be fed into an LSTM model. Alright, so how do we initialize an embedding layer with Keras? There's a few things we have to specify. First off, the input dimension is our vocabulary size that we have to define beforehand. Then we also need to specify the output vector length, output dim. In our example from the previous slide, we chose two-dimensional vectors, but usually we chose much larger vectors as output dimension. The third item we have to specify here is the so-called embeddings initializer. So the weights of embedding layer in Keras are called embeddings weights, and we initialize them like that. A fourth keyword that's quite interesting is the mask 0 flag. So your input sequences in an embedding layer may or may not have different length. So if you think about sentences have different length, and we can use the value 0 as a special value that we can then mask out. So for instance, you start out with sequences of various length, and then you pad those sequences with zeros to make them the same size, only to then mask out the 0 values later on. Okay. Our use case here is sentiment classification for movie reviews. We choose a database of 25,000 movie reviews from IMDb, and those are labeled either as good or bad. This dataset is also available through the Keras datasets module. And the good thing is that the data is already pre-processed as sequences of integers, so we don't actually have to work with the words in a vocabulary, but those have already been mapped to integers. Our task then is to classify sentiment, so good or bad, from the review content. And the way we're going to tackle this is we first embed our sentences with an embedding layer, and then learn the sequential structure with an LSTM. All right, so how do we do this? So we have a few imports, namely a sequential model, dense layer, an embedding layer, and an LSTM. And we also import our dataset. So first off, we specify the maximum number of features, and we set this to 20,000. So meaning we only choose the 20,000 most common items from our vocabulary. Also, we specify a maximum length for our features. So we only allow sequences of length 80, so which would be quite short movie reviews, but that's how we choose it. So then we can simply load IMDb data into memory by imposing IMDb load data with the maximum features as specified to get back training and test data. All right, next, we pad our sequences according to the max length we have specified. So that would mean if a sequence in the training or test data set is shorter than 80 items, we would pad them with zeros at the end. And if they're longer, we'll crop them. Next, we initialize the sequential model and add an embedding layer with the given maximum number of features and 128 output dimension. This then connects to an LSTM layer with also 128 output dimension, and we also specify a 20% dropout rate for both regular and recurrent weights. At the very end, we add a dense layer of a single output dimension and add a sigmoid function, which would specify a value between 0 and 1, 0 meaning bad and 1 good. What's left is to compile a model, which we again do with binary cross-entropy, stochastic gradient descent, and we also have the same accuracy metric as before. Then we fit our model with batch size 32 and let it run for 15 epochs. And again, we use our test set as validation data. Afterwards, we can evaluate our model.